Well, but what I see here now is I see another lens to the left. Right there. So you can have your point bar now on this side. Channel here. About that. This is going to be your cutback side. And then shallow there. Here's your cutback side here. So this one's going to be the opposite. You're going to keep the same sand on different sides. Well, possibly. I think this is the channel. The point bar will be here. And so the channel is on the left. Here's the channel on the right. And the entering. Well, I think we're looking at it. So your channel is wrapped around. So that the cutback is on this side over there, and on this side over there. So, see, what I would be doing is yo me siento a la bodega here, but well, yeah. Well, this is a 3D. One of those, all the way across. That's what it looks like. And then here we go over to you don't know what's off this way. With a little imagination, you can say, well, it looks like maybe it's going to be another guy. Not like that. Another so there's a lot you can do. But there's a lot you can do. You can expand this, you know, and look at the detail, lateral, particular, what side is or you might be surprised. You may see the whole thing. You know exactly where to go as well. See all the guests with that. That's the approach I take. And this again is over.
We always want to still be in because it's thicker. It's oil. Now it's starting to have wow, I wasn't sure. I mean, the point of the water.
Several of the pictures that I'm showing are identical to this. I need to pull up the PowerPoint. And, yeah, so you can look at some of these, and some I haven't shown in my PowerPoint. So the procedure I used here, let's go back and see what I did. The first thing I did is I broke out the shales. I broke out the shales, number one, and then I looked at the pattern, the overall pattern in the sand, and I get the transgression, a little bit of high sand, another sequence boundary here, transgression, and then boom, big sand. Size valley boundary, sequence boundary. So, so that's the first thing, and then we go to the size of it, and you look for the shapes, pattern recognition. And what did we do? We first looked at this one, we looked at the lens, okay, channel here. Yeah, I see these little things here. I bet if you do that, so we did that one, then we went over here, we did the same thing, but the channel now is on opposite sides. So you could have something like this. Like this, where we have the steep side on the left over here, and on this side we have the steep cutback side on the right. That's what you see here. Yeah, that's why you want to do the horizon slice, to be able to just see it. Take all the guesswork out of it, on the horizon slice at that interval. So, now if you look at other lines now, you might be able to see more of what's going on over here. If you look at some of the other lines in the survey, depends on the orientation.
Unfortunately, I only have this image because back then they were trying to display and that
Yeah.
This is, I mean, the fact that this is essentially
Yeah. So shot for different intervals.
So
you don't have the whole 3D survey.
we do now because
I would be doing a horizon slice, and it may show the whole thing.
This one looks better.
Yeah, now, this is the lower, right?
Mm-hmm.
I would take this over here. I don't know what resolution it has, but you know, there are a number of slices. One example I gave you is a fluvial slice that was 4 millisecond, each slice was 4 milliseconds. So, this is a millisecond, a second, or a millisecond? Not depth.
No, this is depth.
This is depth. So, you've got that interval is about about 24. About about 30 milliseconds.
Un programa, si hago esto, sí o se hace sí o no. Sí, programa. Luego ya empieza a hacer todos anotados.
You might see the features like the ones that they showed. So if you went back to some of my points, my previous slide, you'll see several of them that relate just to this. Show things like that.
Yes, because this is we haven't thought. So you weren't sure
Well,
test this
Puede sacar esto de
because the continuity of the chat room some of it
Now, do you get the same, what's your pressure difference between here and here?
what's the
Pressure difference?
we haven't tested so that might be
So you get different, you get a lower pressure out of the red and a higher pressure.
Yeah.
But you haven't done it over there. I see the boundary of those.
So there are differences.
For the very first example I showed, that we did in class, where we had the 5 well logs, and we had different oil and gas. So I put the boundary like that. Okay, this was a gas well. It was low on structure, and then this was an oil well. It was higher on structure. And we found that there was a secret boundary at the edge of the valley. Two different methods.
Y por eso pero la parte de sí, atrás, ser un central debería ser porque eso es más probablemente the only bad thing on the project is it's lower than this
Well, but if you got a fault there, you get trapped right in there. Well, fault contact. That was about if that's the ceiling, you have to check to see if that's the ceiling fault. If it's the ceiling fault, you have your hydrocarbon.
because that would be also
Well, the structural barrier, yeah, but, well, if this is a different sand, then it's a stratigraphic cover here, if it's the same sand, it's just off, full, then you've got a fault zone.
But I mean, if this is an inside valley, if we're talking about these might be some of the.
Yeah, yeah.
So that, yeah.
So I think that makes sense to me, you know, at least a starting point to different looks at the reservoir. Yeah, a different technique.
What you can define here is we want to test it just as it said, after the 3D sites. Well, for me, depende de dónde va el canal. Porque acá, this is dead of that. But it produced a long time ago. Y otra cosa, we're only talking about the transformation.
Well, look, promising. Good. Well, you know, actually, back when since the picture of the new show, really similar, I've actually got one more to show you. Similar to this as well. Can you correlate the shales? I want to try to correlate. What do you mean correlate? No, no, no. I want to correlate on the shales. This one here. Well, let's see now. These are blockier than over here. So, just like the drawing there, we have thinner sands on the point bar side, thicker sands here in the channel. Something like that. There's definitely a difference.
So this will be the other side of the river, like the point bars on the opposite side, and on that part of the
The point bars are going to be here. Here. Point bars will probably be thinner. These will be your lateral accretion surfaces. Oh, I think so, yeah. So those are the things I do. I'd go look at, get 3D horizon placed. And, yeah. And just look and say, you have to really actually see what the
Thank you. Thank you for that. Very
what I'm here for.
After we take because living lines well producing. Perforated. Thank you.
Glad to help. I hope it's correct. Tell me if it's correct. If it's not correct, These are always, this is what I like to do in these courses. See their data, you know, and apply what I've been talking about. This is a good way of looking at it. It's really good pattern recognition. Okay?
You just take the
I'm fine.
¿Una ira salteña? A ver, segundo. Quieren say that about the pizza? Fíjate si queda bien. Para pagar. Llama porque generalmente
Would you be interested in showing this to the group? How we did that? Or it's up to you, it's your data set. Do you have do you have any of that in PowerPoint?
I do.
I think that'd be fun, go back to something that, you know, and go through the procedure. So data that you're familiar with. I'll do that after lunch, yeah. Oh, good, yeah. I think all we need would be the seismic line and that one, we had the gamma log and this one we want. Seismic. That one. We have those three. Maybe this one too. Well, this is good enough.
Okay.
Well, sure. Yeah, why not? Okay. Good. I think that'll be really useful, you know, doing with your own data, yeah, how all of this works. Okay, gonna go ahead and get started. We're almost finished with sequence photography, but we're going to have a special guest speaker after lunch. Julio and I were just working on this project, and at least in my opinion, everything I've been talking about you can apply to that project. And so we can go through with it as a group after lunch and see if you agree with me or disagree or add to it or subtract from it or whatever. So we'll do that after lunch. I think it's a really interesting example. So want to finish up on the sequence stratigraphy. I want to show you this diagram, and what you've got here is a well, gamma ray log and a neutron density log. And a core was taken through this interval, and the geologist determined the depositional environments. Found a sand body up here that was deposited in a nearshore marine environment. Down here, the core showed that this shaly interval there was deposited in offshore marine. You had some estuarian deposits right there, and fluvial deposits down here, and then offshore marine below that. So that was the geologist's contribution to working out, by looking at the core, to work out the depositional environment. Now, let's see. Give me 1 second here to, I'm missing a slide I gotta go find here. So 1 second. Take me a minute here to find this what I'm looking for. Here. You actually don't have that one that I just showed you. I didn't give it to you, but I'm going to show it to you anyway. Well, okay, okay. You don't have this one. I didn't give this one to you, but it's an example that I want to show. Of how now we have gone from the depositional environment. Now let's put that into a sequence stratigraphic framework. What we see, if we start at the bottom, the first thing we see is a sharp break where you've got offshore marine shales below, and then fluvial system and a sharp base. that almost always indicates a sequence boundary. So I'm going to put sequence boundary there. And then what do I see after that? I see a nice blocky sand where the lower part is fluvial and the upper part is estuarian. What does that remind you of? That's Insice Valley, okay, where the lower part is fluvial, and as sea level is rising, you fill the upper part with estuarian sediments. So we have this interval is an Insice Valley fill. Okay. And now if we continue up, what's happening here is you're getting finer and finer grained up. So you're getting more marine influence as you go up the section. So where's your maximum flooding surface going to be? Well, you'd think it would be right here, the maximum gamma ray response. So you could put that as the maximum flooding surface, but you have to kind of use a little bit of geologic insight here. And what I see is above this high gamma ray shale, you get another sand body that's becoming finer up. So I'm really going to, in this case, I'm going to put the maximum flooding surface right there. So there's my maximum flooding surface. I could put it here, but this little interval bothers me a little bit. So I put it there. And then what do I have? I have it getting coarser and cleaner upward, high stand progradation. So this is going to be your high stand systems track. Okay, so now we've been able to put it into a sequence stratigraphic framework, taking it from the depositional environment to the sequence stratigraphy. And this log pattern that you see is one that's really quite common. It defines in many places, it defines a depositional sequence. You've got a sequence boundary here. Somewhere up above your high stand, you're going to have another sequence boundary. And so you've got this internal pattern of finding upward up to what you think is the maximum flooding surface, and then cleaning upward pattern. You see that all the time when you look closely. So what I've shown you here now basically is something like this cartoon right here, where you've got your finding up pattern, got some fluvial deposits down here, maybe some estuarine deposits, and then you get into the gray, which is the marine. Here's your maximum flooding surface, and then everything progrades above it. Okay. So what's the best surface to correlate on? Well, this is the best surface to correlate on. And then you can predict what's going to be above and what's going to be below that surface. And not only that, but you can predict away from the wellbore what you're going to have off to the left and what you're going to have off to the right. Now, just to show you one more example of that, let's see. Well, I wanted to show you one more example. That, oh, yeah, here we go. All right. What I just showed you is a very common pattern that you find on well logs. And it's this pattern here that I just said, where you get fining upward and then cleaning upward or coarsening upward. Okay? When you see a pattern like that, you often find a nice thick sand body at the base, and that's going to be a sequence boundary. It'll be your sequence boundary. You'll have another sequence boundary up here because sea level is regressing. And so what you have, well, it's a little better. You have the fining upward, your condensed section, and here's your maximum flooding surface, and then it reverses itself and gets cleaning upward. Very common pattern that you see. And once you see those patterns, you can develop your sequence stratigraphic framework. So, what do you look for? Well, high gamma ray. Now, it's not really super high in this particular case, but that's going to be your maximum flooding surface. You're going to have a progradational interval that I called it a shallowing upward interval because you're prograding, so you're getting at this site where the well was drilled, at the time of deposition, you were getting shallower and shallower. So you get that pattern. And then below, you get this one deepening upward during transgression. So that spot where the well was drilled during deposition, the water depth was increasing. So you've got your transgressive systems tract. And your high stand systems tract. With your maximum flooding surface. Now, this is what you get, what you guys would probably see all the time because you're working up in shallow water and non-marine. And so you'd be kind of up here in this area if you had seismic, for example. You don't get the same pattern if you're out in deep water because you've got those submarine fans. And so you really do get, rather than a sequence boundary, you do get submarine fans out in deep water. But where you guys are mainly doing your work in shallow and non-marine, this will be the pattern that you'll see over and over again, okay, at different scales too. Okay, so with that in mind, the last thing I want to show you, well, the second to last thing, here's an outcrop in France, and what you can see, this is a long distance outcrop, and what you can see is a bunch of downlap surfaces like that. Those are indications of progradation. So that's going to be a high stand systems tract where you're prograding in that direction. Now, down here is a lot of cover, a lot of material that's sloughed off the walls of this mountain front. So you can't really see what the rocks are unless you get up really close. But when you get up close, what you find is that the rocks below that downlap surface are kind of horizontally bedded, and where that downlap surface meets the horizontal bedding, what you're saying essentially is you're going from transgression to high stand, and so this is your flooding surface, your maximum flooding surface, that yellow line. Now let's apply that to seismic. And here, if you look closely, you can see some downlapping reflectors. It's going to be high stand systems tract. And they're downlapping on this horizontal set of reflectors. That's going to be your transgressive systems tract. So one of the ways on seismic in which you can identify or build your sequence stratigraphy is to look at these patterns and once again try to find the maximum flooding surface. How do you find it on seismic? Well, where you have the downlap pattern onto a more of a flat surface, that's going to be your maximum flooding surface. So now what we've done here on this seismic, we've been able to identify the maximum flooding surface and what's beneath it, the condensed section. And what is that? That's the source rock and that's the seal rock. And then you've got your downlapping progradational high stands above. So in this case, the seismic line, you've got progradation in that direction. So with that in mind, the last thing I want to show you is this. And I'd be remiss if I was talking about sequence stratigraphy and didn't show you this, because this was the original diagram that the Exxon people did to explain sequence stratigraphy. This was their model, and what they have in their model is a sequence boundary, SB, sequence boundary. You've got Insights Valley carving into that boundary. I guess I should have do that over again. Sequence boundary goes like this, and then it cuts down. And that's going to be the Insights Valley up in the shelf area during low stand of sea level. Then you have marine transgression, and you fill up the Insights Valley, and with continued transgression, you're depositing sediments in the landward direction, and shoreline sands are going to form right in this area here as that shoreline moves landward. It'll move landward until you get that maximum landward extent of the shoreline, and that's going to be your maximum flooding surface. And then you've got progradation. Then Then you have progradation and downlap onto that maximum flooding surface. So on seismic, you look for those patterns, and you can do a sequence stratigraphy framework there. second, I'm having a problem. So, here we have, I have an arrow here showing transgression in the landward direction. There's your maximum flooding surface with the condensed section just below it, and there's your downlapping high stand deposits. And you can see these sorts of patterns on seismic quite frequently. So you develop a sequence stratigraphic framework that way. On well logs, what you do with the well logs is what I showed here. In the well logs, you look for the pattern where you get the shallowing up and the deepening up, and the boundary being your maximum flooding surface, your high gamma rate. So that's how you can do with well logs, a sequence stratigraphy. On seismic, you can do a sequence stratigraphy interpretation. Okay, so the very last thing is this. This was the original Exxon model, where you had, I'm just showing now the transgression in green, the maximum flooding surface, and then your downlapping high stand deposit. I'll skip that one. So now I've just kind of colored this in, where the question would be, now that I've developed a sequence stratigraphic framework, where's the sand? Where's the reservoir? Where's the seal? Where's the source rock? Well, I've drawn in yellow here where the sands are going to be. If you're out in deep water, you're going to have nice submarine fan sand shown in yellow out here. Let's see, this is submarine fan sands there. Not going to find too much up on the slope, but you get into the incise valley, you're going to find sands there, and then these transgressive shoreline sands. So that's where you, and then during progradation, when you form your delta, you'll form delta sands down near the seaward edge of the delta. So you can predict where your sands are going to be. Can you predict where your seal and source rock is going to be? Well, yeah, you can. Maximum flooding surface, right. So there's your source and your seal. So that's the Exxon sequence stratigraphy model. And that's about where I'll show this one more picture, and then we'll move away from the from sequence stratigraphy. This is a diagram just to illustrate how you can use the maximum flooding surface in condensed sections for regional correlation. And these two wells are a couple of 100 miles apart. Well, actually, this is an outcrop section here. And this is, this is the outcrop. And then there's a well log there. So some geologists came along and they looked at the outcrop and they developed a sequence stratigraphy. So they said, well, I wonder if we can find the same sequence that we see in outcrop, can we find it in this well we just drilled? Okay. So, what do they go to? What do you always go to? You go to the shale. You look for the shales, and in this case, they found 3 shales. One there, in the outcrop, one there, and one there. and they use that to correlate. And when they went to the well, they found a shale here, and a shale there, and a shale there. So they said, well, okay, you find 3 shales up in the outcrop, you find 3 shales in the subsurface, well, so they must be the same, so we'll just connect them up and correlate them. And you can do that, but again, if you've got the paleontology, it's better to look for fossils in those 3 shales. And if you've got the same fossil, say in this shale that you do have there, and this shale there, and then a set of fossils here and there, well, then you can be pretty confident, the same set of fossils, you can be pretty confident that those 3 correlate. So now you've done just by identifying the condensed sections and realizing that they're usually very laterally continuous for long distances. They're marine shales, blanket-like shales, and if they've got the same fossils in a shale from 2 different wells, you can correlate them. So over a couple of 100 miles, they're able to do the correlation here. And again, you can do it by just counting the shales. Say there's 3 shales here, 3 shales there, but it's better to back that up with something like the paleontology. And if you get the same microfauna here as in here, then you can make that correlation line. But suppose, for example, that you find a set of microfossils here, and you then go down to the subsurface well and find that same set of microfossils down there. Well, your correlation line is now going to be like this. So this upper interpretation would be incorrect. And so now you would correlate this shale with the shale down there. So it's good to kind of corroborate your interpretation with as much data as you can. If you've got the paleo or the palynology, that's one way to do that. To kind of verify or strengthen your correlations. Okay, well that's all I wanted to talk about in sequence stratigraphy. Bottom line, sequence stratigraphy, it allows you to develop a sequence stratigraphic model that allows you to predict where within a stratigraphic section you're going to find reservoir rock, seal rock, and source rock. And that's really the fundamental thing. And we've gone through that now. You haven't done in deep water, because I don't think any of you are working in deep water, and my lecture there is really long, so I want to skip that. And what I'd like to do now is give a relatively brief lecture on unconventional resource shales.